Hi, I recently just upgraded the motor on my mill with the Chinese motor that came with it to a Baldor, and a lot of reasons for that, not the least of which is I couldn't set up the VFD right with the Chinese motor. Not sure exactly why that is. Perhaps some of the rated specs and whatnot weren't exactly what they should have been, and the automatic setup function on the VFD that's trying to adjust its parameters automatically couldn't sync up with the motor, and so there was always kind of a problem. It was an oscillation in the motor speed, and inevitably I just swapped out the motor, and that's probably the topic for another interesting video. The motor size is a 90L. Well, let me just show you what we got here. So this is my mill. It's Industrial Hobbies. It says it's a CNC, but it is not. It is a manual mill, and as you can see on top here, I put a Baldor 90L metric style motor. It's smaller than the original Chinese motor. It doesn't have a separate fan on top. It uses the rotation of the spindle itself to generate the airflow to keep the motor cool. So I've got a number of sheets that came with the VFD, and I should just start out by saying I was successful in getting it to sync up with this particular motor. I don't notice any of the same sort of oscillations, or especially when you adjusted the speed kind of toward the slow end. Now, and I've got suspicions of why that was true. In any case, what I'll show you here is how to set up the VFD. Now, what I've got is a separate emergency power. I just shut off the VFD actually by pressing that. Separate run and forward and reverse, and I set those things up myself. You can basically apply any kind of control configuration that you'd like personally to a VFD to control your machine. In this case, I just felt it was kind of okay to put I had these switches laying around. I had these IEC weatherproof boxes around. I have a contactor in the back and another box here, and I just mounted it all on a 1/4-inch thick aluminum plate, bolted it to the side of the machine here. Again, you've seen different configurations. People do this in a lot of different ways. So what I'll do is let me turn the VFD back on again, and what I'll do is, I mean, you know how these things run. I mean, I hit the go button, and there's the spindle is running. I can reverse it, and it will come to a complete stop. There's a pause, and then it runs again before it reverses. And so, I got, and then also, I've got kind of an infinite speed control. So it'll run pretty darn slow without too much difficulty. And then if I really wanted to run it that slow, I'd shift gears and actually run it at a higher speed. So if I really wanted to run it that slow, I'd put it in low gear, and I could probably get down to 1 revolution a second if I do it that way, see? I mean, I don't know what you'd use that for at a mill. Turn your mill into a clock, perhaps, but that's how that all works. And then I go, if I went for full speed, kind of loud, which is another reason I swapped out the Chinese motor, because the Baldor is a lot quieter. If you can believe it, with the Chinese motor, it was even louder than that in high gear. You can't hear yourself think. You got to wear ear protection. I noticed that there are guys who do videos with those Bridgeport style mills, and they can be running and talking and listening to music at the same time, and this is not that. Now, Industrial Hobbies has upgraded the gearing in the head of this mill. This is a Rongfu 45, basically, and part of what they do and part of how they sell this thing is they throw out all the original Chinese gearing and they put their own in. So I understand this is actually smoother running than the original. I don't have a copy of the original, and I've never run one, so I couldn't tell you. But they say this one runs smoother than the original. It's, it sounds like the gears mesh just fine. I mean, you don't hear any grinding, or bearings are supposed to be upgraded, et cetera, et cetera. This one has a NT or Cat 30 style spindle in it, so I can use the Cat 30, all the Cat 30 adapters and adjusters, and it's supposed to be a bit stiffer than the standard what comes with the RF45. I don't even think they have an R8 with the RF. I'm not entirely sure. At any rate, what I want to do is show you what we do here with the and how I set up this VFD, because I think this is kind of a mystery. Now, there are probably, oh gosh, there's 20, 30 pages of parameters here for this thing. Now, these are made for industrial purposes. So somewhere in a factory on a production floor, this thing is running a conveyor belt or a motor, some machine, some fan, and they're all different applications that it can be set up for. And there are different power requirements, there are different speed requirements, different torque requirements, and you can adjust all of that with this one machine. This happens to be a Teco 7300. It's the ubiquitous cheapo VFD. You buy these things based on how much current you want them to source. So what they'll say is how many horsepower of a motor that it'll handle. This is this will handle a 2-horse motor. This Baldor motor is a 2.2 kilowatt output, basically about 8 amps input, 3450 RPM, 230 volts. It'll also run in 460 depending on how you configure the coils inside. I've got this thing wired for what they call low voltage, which is 220 or 230, and it doesn't change the speed and whatnot. So when you're looking at setting this thing up, and I'm going to presume that you've already wired up your motor and you know Y versus delta, and you've got all that under control, and you've done your connections here. I just want to show you how to program it, otherwise this will go on forever. Alright, so you program the VFD by first hitting this what they call DSP or function button, and you wind up getting these 3 or sometimes 4 digits. 4 digits can correspond to a bank and then a specific parameter within the bank. So in this case, 0, and you've got to have the manual to know this. I mean, let's see if you can see this. So 0 is for drive operation mode. That's 0 right there. And function 0.00, 0-00 is control mode. Now, we're in vector mode. Vector essentially means that for a given speed, we want a continuous torque. We don't want this thing to slow down and get weak at the same time. The way these work is they're taking a single phase, or in the case of 220, 2 phases, but it's basically a single phase. And they're converting it to 3 phases. And they're doing it with a series of inverters and transistors, and inevitably that's a lossy process. They're sending pulses or sine waves, 3 separate sine waves, to this motor to create a rotating magnetic field. These motors have a stator on the outside. This is an induction motor. There's a stator on the outside which consists of a number of coils. It'll be a multiple of 3, so I believe there's 6 or 9 coils in here. And those coils are connected directly to the VFD, and the VFD drives the current through those coils, which create a magnetic field. And if you go and look on YouTube, there are plenty of discussions of and animations of rotating magnetic fields, and it basically creates a rotating magnetic field. The rotor inside is not physically connected to the stator in any way. It's on bearings, it sits in the middle, and what happens is as the magnetic fields rotate, they generate a mirror image of themselves, sort of, in the rotor, and the rotor winds up getting pulled along with the rotating field. There's a bit of a delay with that. It's called a lag, and if you didn't have a lag, you wouldn't have a induction motor. And We don't need to get in that theory here. You can actually YouTube it and see a plenty great engineering picture of how an induction motor works. What you need to know here, though, is there's 3 coils being run by this. So vector mode says I'm running those 3 coils, and when I want to have a low speed, I don't want to decrease the oomph, the power of the motor, the torque that the motor provides. So it plays some games internally here by providing perhaps stronger pulses of AC positive and negative that will keep the torque as close to constant as possible when you slow it down. When you speed it up, you don't want it to, you don't want it to blow itself apart. So basically, you want to keep the torque constant across the entire power band. And that's what vector mode is trying to do. There's a vector mode where you have variable torque, where you're actually, as you slow it down, you do weaken it. And then there's a mode that they call volts per hertz, which is perhaps whatever you're driving is expecting a power supply where the voltage of the power supply is also regulating the frequency. We don't want any of those things for this. We want general purpose vector drive. We want the torque to remain constant across the band. So we're going to choose, and it says here, all right, so in order to get, vector general purpose is what we want. We'll stick with the factory setting, which is 0, 0, 0, 0. So what I'm going to do is if I say read, I push the read button, and I see 0, 0, 0, 0, that's the factory setting. Now I could change that. I could say, oh, give me 1 or give me 2, because I've got, if I change it to 1, that would be vector with variable torque. If I change it to 2, that says volts per hertz mode. We don't want either of those. We want to stay on 0, so I'll press enter again, and it says end. All right, so that's that parameter. The next 5 parameters here are the ratings on the motor itself. And you can get these off on the nameplate on the motor, and you can just enter them. So what I did was, if I go and I press the up and down button to change the parameter here on the VFD. You can see that. Get my finger out of the way. All right, so we're in bank 0. We got parameter 0, 0. We've chosen general purpose vector mode. Now I'm going to hit 1. And that particular parameter is motor rated voltage. So if I take a look at that, the way I've wired up the Baldor here, I've wired it up for 230. It can be wired for 460 or 230. I've wired it for 230. And so that's what I've entered here. I could change that. I mean, I could change it to 220. I could change it to whatever I want. But the bottom line on that is that the motor is a 230 motor in this wiring configuration. So we're going to leave it that way. And it recognizes that. Now I press the up button, I get the parameter 2. I say, let's look at that, and I got an 8. Parameter 2 is motor rated current in amps. So max current for this motor in 230 volt mode is 7.9 amps. No, I put 8 in. I could put 7.9. It wouldn't hurt anything, but for some reason round numbers make me feel better, so I left it on 8. And you can see that 8 there. Okay, so I'm entering. Just make sure you can actually see. Yeah, you can see that. All right, so if I go to parameter 3, 003 is what's the rated power in kilowatts? Well, it's 2.2 kilowatts, so that's good. I entered that. Parameter 4 is what's the motor rated speed in RPM? This one is rated at 3450 RPM, full speed. We can get into how a synchronous motor as a special case of an induction motor always runs at an integral frequency of the source power. In this case, 60 hertz, so it would run at 3600. With the way these things are set up and the way this motor is set up, it's optimized to have the rotor running slower than the rotating magnetic field at power rating, and that fact that it's slower, that slip, I think I called it lag before, but it's actually called slip, actually generates the power. And synchronous motors have power too, but this generates it through the slip. So it's actually the rotor's in many cases running slower at full speed than the rotating field, and that slowness actually generates the power in the rotor. So we left that at 3450, which is what it says on the nameplate. All right, I want to leave that there. And then if we go to 5, what's the motor rated frequency? Rated frequency 60 hertz. Now this is where I had a problem with the Chinese motor, because the Chinese motor said it was rated between 50 hertz and 100. I tried entering in everything from 100 to 60. You know, one thing I know for sure is you know, my input line supply is 60, so I tried 6, didn't work. I could tune the motor at 45 hertz or so, or excuse me, 55 hertz or so. It was a strange number, and it never worked right. And I'll explain tuning in a second. Actually, explain it right now. So you enter in all those values. I'm going to skip parameter 6, and I'm going to go to parameter 7. I'll show you why. So parameter 7 is my input line voltage is 220. Or 230, I entered 230. And then the last one, parameter 8, is your language selection. I speak English, so I left it on 00 as English. But this thing isn't talking to you in any kind of language anyway. It's just giving you numbers, so who cares? All right, let's go back to parameter 6. So parameter 6 is auto-tune. And auto-tune is not what it is in modern music today. But it sort of is, you know, in auto-tune modern music, your voice is adjusted to a pitch based on you know, if you're off pitch, it'll raise you and lower you in key, et cetera, et cetera. And this will do kind of the same thing. What this is trying to do is the coils in that motor have a certain resistance, they have a certain inductance, most importantly an inductance, but they have a resistance, an inductance, and a self-capacitance. That presents what we call an impedance to this drive box. So this is trying to drive the impedance of that motor. And you know, think of impedance as a resistance, as you know, as kind of like an inertia in some way. You know, if you want to push somebody on a swing, they have an impedance, and you know that if you've got to push them, and they'll go up. Now, if you push them out of sync with their swinging, they go nowhere. Or, you know, but you know, if you push someone on a swing in time with their swinging, that swinging motion can build up and up and up. That's called resonance, actually. In electronics, there's also resonance, but what you're trying to do here is, it's also called impedance matching. You're matching your power output to the power input that can be accepted by this thing. So in auto-tune mode, what this is trying to do is, it's looking at all the parameters I've given it, because it doesn't know what motor, it doesn't know the parameters of the motor that's up there. It just sees what's connected to the wire. It feels what's connected to the wires. And I've told it what the ratings were, what the manufacturing ratings were. So that gives it a starting point. But what it's going to do now is it's going to actually send test pulses into this motor and figure out what's the best way to push this motor? What's the best frequency to push it at? How do I get the maximum power transfer between this box and the coils in that motor? Now, the way I do that is, as you see, if you look in the manual, it'll say parameter 6 is auto-tuning, and it has two values. It can either be 000, which says invalid, or 001, it says valid. Well, that's kind of odd, but you know, the manual is written by people who have a good grasp of English, but it's not their native language. It made perfect sense to them when they wrote it. If you press invalid and you just say enter, nothing happens. It doesn't do anything. But what I'm going to do is I'm going to go into this parameter and I'm going to change it to 1. I'm going to change it to invalid, and I'm going to tell it that it's got an invalid set of internal motor parameters, and it's going to try to match it automatically. Now watch. So it goes into this AT mode. I don't know if you can hear that high-pitched, right? So it just checked out the motor, and if it was able to tune it, it'll say and then it'll go back to this, and it was. It's able to tune the motors. So now if I turn it on, it sounds just peachy. And in fact, I can slow it way down, and I don't have any pulsing, and I can turn it up, and everything's fine. So that's drive operation mode number 0. Now, there are other things in here I can go over too, and let's just for the heck of it, we'll go to another bank. So I go to another bank by pressing this reset button. It says reset, but the arrow is pointing that way. So now this guy is flashing, and I'm going to go to bank number 1, and I'm going to enter, and you see I have value 1 for parameter 00, and that's run control source selection. I have set it to 1 because I've got an external run and stop control. You can see that in the manual, and I've got an external stop and run control, which is this. I've wired this switch into the Teco, and the Teco's got a whole bank of wire ties or wire hold downs that you can put wires into that basically allow you to adjust the different functions of the VFD from external devices. So I'm turning the thing on and off. I'm adjusting the run by a switch that I created. Actually, just for fun, I'll turn that back to 0. So I turn it to 0, I'll say enter. Now my run switch doesn't work. However, the run stop button works. See that? So there's a button on the VFD itself for run and stop. Now it works. So what I'm going to do is I'll go back and turn my switch on by saying go to the external, enter. Now my switch works and this doesn't. There are other parameters on here too. So parameter 1-01 is for forward reverse. I've got that set up with this switch right here. You can do things like say prevent it from ever getting into reverse mode, prevent it from ever starting unusually. You have keypads, start and stop buttons and whatnot. So I've set all that up so that it controls this appropriately. The other thing in here is the control of the frequency source. Now, controller frequency source is parameter 6. Let me go to that one. So I have 6. If I say enter, I've got that as the potentiometer on the keypad. Yeah, this is hard to see. Yeah, potentiometer keypad is parameter value 1. So it's parameter 1-06 value 1. I've set that to 1, and what I'm saying there is when I want it to be able to speed up and slow down based on my turning this potentiometer. What it also indicates is that you can have an outboard potentiometer somewhere. You could set one up anywhere that's convenient for you and adjust the speed, somewhere else that you like. So that's the start and stop functions. Now go back to there. Bank number 2 is for manual and automatic restart modes. So, for instance, with bank number 2, one of the things you can do is what I've done here. So, if I'm in run mode, turn that on, I hit the emergency stop, it stops. Now, if I was to turn it back on but leave the switch on, so I've hit the reset, I've reinitialized power, but I didn't turn the run switch off. That's not going to start up on me, so that's a safety feature. So I got to turn it off to get it to go again. And I guess we got to wait until it gets out of this mode here. There we go. So that's a safety feature. And you can say, and that's in parameter 2, momentary power loss and restart. You can disable it. You can enable it. You can say there's something called momentary power loss ride through time, which if the power goes out, how long do you want it to stay active? You can actually have this Teco box will stay alive on the basis of its internal capacitors for a minute, and so you could have it set up to be shutting things down for you. If you're in a factory and power goes down, but you're on battery, you can have this guy shutting down various things that it's in control of while the power's off. So you have this ride-through mode. There's restart delay time, which says, okay, after there's a power glitch going off, and then power comes back on, maybe you don't want everything to turn back on right away. You may want to put a delay in there, and you could do that. And actually, in my case, the power loss is being caused by me hitting the emergency off button. So I want it to come back right away. There's a number of restart attempts. Do you go to direct running after power up? In my case, I don't. I go to I disable direct after power up. There's something called kinetic energy backup deceleration time, which is really interesting stuff. I'm not using any of that. The other things that I'm using quite a bit here are the operating parameters, which are here in bank number 3. And the operating parameters are things like, okay, what's the upper frequency limit for this? Meaning, if the Teco varies the speed of the induction motor by changing the speed at which the rotating magnetic field rotates. It does that by changing the frequency it's providing to the motor. So here we all are worried about 50 hertz motors, 60 hertz motors. This thing is never seeing 60 hertz. It's seeing some other value based on what speed I have it set to. The manufacturer's max is 60 hertz, and there's a lot of reasons for that. It's tuned for 60 hertz. If you try to run this thing outside of 60 hertz, even slower or faster, you're going to get impedance changes that make it harder to transfer power. And that's why, in fact, that's why there's that automatic auto-tune. It's trying to find a balance in between bad impedances where it can operate and still speed up and slow things down. Because if you're a 60 hertz motor and you're optimized for a 60 hertz supply, you get theoretically the best power transfer. When you start slowing down the frequency or speeding up the frequency, you get with an impedance mismatch, which means a lot of your power is going nowhere. It's just heating something up, or it's not going anywhere at all. And so what you do here with the upper limit is you say, look, never in any case, you should never send my motor anything greater than, in my case here, I'm saying 70 hertz. If this thing runs at 70 hertz, actually runs at 60 hertz, I know I'm going to get 3,450 RPM. So 70 hertz is going to give me, 15% more than that. In fact, it's going to give me about 4,000 RPM. Now, the motor, I don't know how well the motor likes 4,000 RPM. The power transfer is not optimal, but I can do it. It's kind of like overclocking your PC. Back if you're a gamer and you're trying to get the maximum power out of your PC, and I'll show you for a second here. Right. So what I'm going to do is I'm going to let's go back to. There we go. All right, so here's frequency mode. So I'm going to turn the frequency up on here. So I'm running the motor at 4,200 RPM. 4,200 RPM, that's 70 hertz. So not such an efficient power transfer. The motor's probably going to heat up quite a bit. I don't want to run it that way a lot. In fact, I may not want to run it that way at all. But there may be some reason where I'm milling something, with small bits, and I just want to do it for a little while. So that's what the upper frequency and upper and lower frequency limits. It has a lower limit too, and the reason it has a lower limit is just what I said. If you go too far below the rated frequency, you wind up with ineffective power transfer and an impedance mismatch, and so the motor probably heat up for that reason as well. That's another reason why you don't want to run this thing at too low a speed. Like for instance, here I am running it at 257 RPM, which is let's do an easier one. So if I run it at 3,500 RPM, I'm running at 10% of my rated speed of 3,450. That means this thing is being fed with a 60 hertz, or rather a 6 hertz, instead of with 60. So that's probably going to wind up, even though it's running very slowly, it's adjusting the current so that the torque is still there. This thing is probably going to heat up. The fan isn't moving too fast. So really, if I want to run this thing slow, the best thing to do is to leave it in the mid-band and use the gears. Just slow it down with the gears like you normally would. All right, so other parameters that are interesting, acceleration time and deceleration time. What you can do is, if I go to parameter 3 2 is acceleration time. Enter. I've got acceleration time at 0.1 second. That means it's going to try to get up to full speed in 0.1 second. But let's say I wanted to be a little bit more gentle on the gears, and I said, all right, you could take a half a second to speed up to full speed. I don't really want to do that, but let's say I did. So I hit enter. Now watch what happens when I turn this on. It'll take a half a second to speed up. You'll hear it. Here I went ring. Actually, let me give it something more extreme. I will give it 1 full second. We're going to give it 1 full second to speed up. So that. So it definitely takes a while to speed up, and that's, you know, probably reducing the stress on the internal components, etc. In fact, you know, half a second isn't a bad idea. I'll leave it at half a second. Parameter number 3 is the deacceleration time. Hang on. 3 deacceleration time. Yeah. And I got to set that one correctly. I've got it set. Somehow I've got that set wrong by a lot. That thing is up to. It's got deacceleration time at. Good God, it's like an hour, 3,600 seconds. So we'll fix that. It does work. Now, the other things I'll say is there's S-curve. So if you're driving a big load and this thing was running, you know, a motor that was, you know, who knows, is handling a loader or something where you don't want to deaccelerate too quickly because things will get stuck. The gears, you know, there's too much inertia in the gears or whatever. You can actually deaccelerate along a curve, and what that means is you can deaccelerate smoothly first, slowly, and then faster as you go. So if you're going to take a second or 2 seconds to deaccelerate, you could adjust that here. That's probably way out of the realm of what you and I are trying to do here. We just want the thing to shut off when we turn it off. Now I'll go past. There's jog. You know, then there's. If this was a lathe, I've got jog control. I can set jog deacceleration, and I don't. I do have it on the lathe, and I do have the jog set, a jog button set up. There's something interesting called DC injection brake start. Now, what that means, and its use on this is very debatable, but I've set it up when I bought the thing because I didn't know what I didn't know. And basically what you do is, I'll show you, you put a device like, you can see that green thing there. Let's see back here behind the, there you go, that's a resistor, this guy right here. All right, that's a big high current resistor. And what that does is shunts off the current supply when you shut the motor off. So essentially, when you hit the off button, what it's going to do is it's going to take the power that was going into running the motor, and it's going to dump a lot of it into this resistor. Now, turns out you don't need the resistor. If this was like an electric car, where I had the mass of a car, and I take my foot off the accelerator, and I need the motor to slow down because it's not going to slow down on its own, you have that resistor there that basically acts like the brakes in an electric car. It's completely unnecessary for this. The thing will slow down and stop on its own just with the friction of the gears itself. So we don't have to worry about that, and you do not have to have one of those. However, one of the interesting things it'll do is a DC injection brake. So what you can set it up for is, as it's spinning, if you want this thing to stop really fast, if you're turning let's say you've got a big boring head, or you've got a shell mill that's got some mass to it, and for some reason you want to bring that to a halt more quickly than it could on its own, you can adjust parameter 3-11 to inject some reverse current into the spinning motor. So what it's going to do is, as the motor's spinning, you hit off, it will inject current to actually try to reverse it. So not only is it going to cut off the torque, it's actually going to try to turn it backwards slightly. Now, it's not going to turn backwards. It's just going to watch itself slow down, but it's going to slow it down with a current. And that's an interesting thing to do. Now, here on the mill, I don't have any reason I don't have anything that's so massive that it's got so much inertia it's going to keep that motor spinning just because just because it's on. I don't have a bit that big. I don't have anything that big here on the mill. However, on the lathe, I've got an 8-inch chuck, and I could put a big pipe in the 8-inch chuck, and I might want to stop that a lot faster. Now, I don't have a foot brake on my lathe. I don't have a friction brake to stop it. So the DC injection really helps there. It acts like a foot brake. So when I shut off the lathe and hit the off button, the VFD tries to reverse the chuck, and there's a lot of mass in that 8-inch chuck. It weighs 80 pounds or 60 pounds. So there's a lot of mass there, and whatever I'm turning is part of that mass. And I may want it to stop really quick because maybe, I don't know, maybe somebody got stuck in it, or or my tool is flying around, or who knows what it is. I got a chip that's about to hit somebody in the eye. I want it to stop. I want it to stop, and so it'll inject reverse current, and that's these parameters here. You can set how long it injects reverse current, the level, the strength with which it injects the reverse current, and when it starts injecting the current. You could actually say, don't start injecting reverse current until I turn it on. Wait a half a second. I don't know why you do that, but if you're in a production mode, you need those things. For us, we don't really need it. Okay, other things it's got here, parameter locks. You can actually turn off these buttons so that you can't actually accidentally press them. There's controls for fan. There's energy saving modes. Bank 4 is digital display mode, and right now I have this thing when I turn it on. That was interesting. I've set some parameter that shouldn't have been set. So right now, when I turn it on, I'm in a mode where I'm looking at the RPMs, and let me check that out. That was all right. I found out what that was. If you remember, I was looking at that deacceleration time parameter, which is 303, as you see there. Take a look at it. It was 3,600 seconds. So I was shutting it off, and it was going to wait 3,600 seconds to shut off. Actually, what happens is it's set to 0.1 now, but if I push this down button, it goes immediately to 3,600. So I must have accidentally pushed that down button. Now it's set right, and what I can show you here is that yeah, I got that. If I go back, so I've got it set in a mode now where it's showing me the RPM that I'm driving the motor at. So it's like 2718 now, and I could set it down, so that's all controllable from this digital display mode. Am I going to show the current that it's providing? Because maybe you're at a constant RPM, so you want to show current, and the current would change if the load changed. DC bus voltage display, you can see what's coming in on the bus. Actually, that's the driving bus, and how it's displayed. Is it 3 digits with a single decimal, etc., etc. Item 5, or bank 5, is for all of the multifunction input terminals. And you know what? Let me open this up and show you the inside and show you how we wire these things up. Of course, I got to figure out how my camera works. Okay, so let's just, there's a single screw. Take that off. I'll try not to electrocute ourselves because this is live. So what you have here are on top are selectors for the switches, and so these are different. These are my on-off switch and my reverse and forward switch are coming into this bank of wires on the top. As you can see, I've only got 3 things hooked up here. There's 3, 6, 9, and then there's another 3, 6, 9. So there's 18 different connections for all kinds of different things you can set up. There's whether you're setting this up, they call it NPN or PNP mode. What that means is if I'm going to turn the thing on, should it be on if the control voltage is high or if it's low? That's what that means. And then there's default settings for the switches here. This is for a remote head. Actually, you can take this head out and put it somewhere else more convenient. That's what I did on my lathe. And then underneath here, what you've got are all the high voltage connections. So the input power, basically you've got the input power, you got ground, and then you have the three phases leaving here into this 10 gauge wire that I've set up. So you've got a bank of controls and the high voltage power supply there. So that's how that works. And with item 5, you're controlling all of those green connectors, the wires in the green connectors, and they can be any sort of thing. So you've got all these terminals, and you can say, well, make one my forward and reverse, make one for jog, make one for control signal selection or command selection. I mean, there's all kinds of interesting ways you can set this thing up. Let's see, bank 6 on here is for jog and preset. Bank 7 is for analog input selection, and that's just saying, for instance, if you had a speed control, a remote speed control, which I do on my lathe, I have an external potentiometer that's not this one. It's one I have on the front of the lathe, and it says how much voltage. You set the voltages and whatnot, and the range, what this voltage means this speed, etc., etc. And there's, you know, more interesting things about relays and whatnot. The bottom line of this device is it is way more configurable than someone like me, a garage shop guy, needs for any reason. I've got this controlling my mill. I've got one controlling my lathe. I had one controlling the rotary spark gap on a Tesla coil. I never use, you know, I use maybe a quarter of the setups here, and you're perfectly fine leaving them alone. If you don't touch those setups, nothing happens generally. If you don't know what it means, you can just leave it alone, and things generally work. So that's, yeah. And then there's, you know, communications mode, whether you can hook up a RS-232 serial connector to here, and you can turn things on off from your laptop if you wanted to, or your desktop right beside the machine. That's what you'd do if you were going to use this VFD in a CNC, because connecting this through RS-232 to your serial port would enable you to use Mach or something like that to change the head speed dynamically, and that's how they do it. So, you know, you can go from 38.4 down to 4800 baud, stop bits. There's then it gets into what all the auto tune parameters are. So if we actually wanted to see, when I did auto tune, what parameters it picked up, that could be sort of marginally interesting. I have to go to 14 here. 14. So 14 resistance is the stator resistance. That's the coils on the outside of the induction motor. It found 215 ohms. Right, and that's really variable. The stator resistance is going to depend on what kind of wire they used and what manufacturer it is. It's probably going to be different for every motor, maybe even within the same manufacturer. So that's the stator resistance. So if we go to, let's just see, number 1 is the rotor resistance, and that's even more interesting because the rotor is not connected electrically to any of this. The rotor is connected magnetically to the stator. There's no wires going to it. So it figured out by sending pulses and seeing the resistance of those pulses that the correct equivalent resistance to use for its internal settings was 262 ohms. I didn't have to set that. Now, if I had to set that myself, I don't know how I would figure that out. I mean, there are, you know, I get a frequency generator, and I could, you know, there are ways motor shops to do things like that. But for me to figure that out as a layman without the right tools would be really, really, really difficult. If I go here to, and there's no, by the way, there's no reason to change any of those things. There's nothing to be gained and everything to lose by tweaking those parameters. I can't imagine there's no good can come of that. I'll just leave it at that. So 14.2 is the equivalent inductance, so 821 millihenries. If you don't know what a millihenry is, don't worry about it, but that's basically the resistance of a coil of wire. It's the reactivity of a coil of wire. It's a resistance to AC. It's what alternating current sees and not direct current. And someday I'll make a video about all that cool electronic stuff. Okay, and then even more neat for you electronic wizards out there, is the magnetizing current is in amps AC. So the magnetizing current is 4,100 amps. That's pretty interesting. What that's saying is that you get an equivalent of 4,100, and there are Maxwell's equations you can use to figure out exactly what kind of force you get out of that. But the let me just make sure this is not milliamps. No, it's amps. So that's the current, the AC current that's needed to drive this motor at full speed. Now, you're not getting 4,100 amp. You don't need a 4,100 amp breaker in your box. You don't have to worry about the wires being rated for 4,100 amps. This is a theoretical maximum here. It's a measurement, mathematical measurement that helps us understand how it generates torque. It's just kind of cool that you can see that. And then ferrite loss. So this is saying, this is interesting. So there's 205 ohms, or actually it's conductance, so it'd be 1 over 205 ohms. So what that's saying is when it's the magnet in the stator is a coil of wire around a ferrite core. There's some inefficiency in that. What happens is when you magnetize the ferrite core, it doesn't magnetize and demagnetize immediately. There's a hysteresis to it. In addition, and the hysteresis provides a back current, so it acts like a resistor, even though it's magnetic, and that shows up as a loss. You have to actually get past that resistance with some current before it'll do any good. And what that's saying here is the conductance is 205 mhos, which is not so bad because that means the resistance is 1 over 205 ohms, which is nearly nothing. So this motor is a very efficient motor, and I'm glad I bought it. Okay, I won't go into the other things, out of range modes. You can set maxes and mins. You can set function resets. You can say, after it's been on for so many hours, shut it off and don't turn it on until you hit reset. And I don't think you need to worry about that. The main thing, as I showed you, is kind of I know I went pretty fast, even though this was a long video. How something like this could be set up by someone like me, a layman like you, to work perfectly effectively in this particular mode in your garage. You're not setting up a production floor. You don't need to worry about 3/4 of these parameters. But the ones you do have to worry about, you got to worry about, or things won't work right. Anyway, I'm Joe. This is my garage, and thanks for watching if you watched this far.